Hello, how's it going? Hope you're well. In this video, I'm going to look at multi-threading, of course, and I'm going to look at making threads sleep and wake up. We're going to have like a job system, so we can have a bunch of worker threads sort of sitting in the background doing nothing, waiting on some work, and then when they get work, they consume it and do it. So to start with, this is going to be an overview. Like, I won't be doing this line by line. That's crazy. That's too much. But I will be talking through the concepts. So to start with, I'm going to run through this single-threaded version just to show how the job system is going to work for this demo. So actually, let me just run this. All right. So I want to set up some jobs. I'm going to dispatch 9 jobs. There we go. They're completed. I'm going to dispatch 90 jobs. There we go, they're completed. Put in a negative number to end the program. So the way this is working is pretty much as you would expect. We grab the number of jobs that we're going to commit, and then we just loop through, keep adding them to a work queue, and then we just keep going through that work queue and executing all of the jobs. Now, the work queue is pretty much a linked list. So to add things, we just insert onto the linked list. We can search through the linked list, find the first job which is pending, which hasn't been completed. Okay. We can also check if the queue is done by looking through and seeing if there's anything which isn't complete. And we can also clear the queue. And really all that's doing is just stepping through deleting elements. Okay, great. So then we have this job, and this job really, it's in this virtual function here. So the reason that I'm inheriting this is I find it's useful to have a general abstract class with just some concept of like, this is some sort of job. It has some sort of execute function which doesn't return anything. But then here we have the actual concrete instantiation of that. So all we really do is just print out we got complete and set our status. Anyway, all very exciting. Now, just to benchmark, okay, this is fine. We can see we are using 1 megabyte of memory and almost no CPU. If we go run that, we can see that we are now using some CPU and memory. And that took about 59 seconds. And we can see that once everything's completed, we just get rid of it. Okay, great. And we can also launch more jobs if we want. All right, so let's have a look at multi-threading that. Here we have a naive multi-threaded implementation of this. First of all, I get the number of threads which I can support. This hardware concurrency will just straight up give me the number of threads my system can support. Then I'll subtract 1 because, well, we already have 1 thread running. So then we'll go ahead and launch all of these threads with the, this std thread constructor, as you've seen previously in the series. The way this thread will work is we take a reference to the work queue and we take a reference to a Boolean flag, basically to indicate when the thread should end. We initialize those. We also save the thread number. When it comes to running the thread, of course, we'll just signal that the thread is like ready to go. And then we have this infinite loop. Well, it's not infinite. It depends on the done value. But this bit is infinite. So what we'll do is we'll try to grab the lock. If we didn't succeed, then just continue, try again next time. And yeah, I have a few other checks here. So if we've got the lock, but the work queue has no jobs ready to go, then just continue. We're fine, we're good. And otherwise, well then, we'll just grab the next job and complete the job. Now, this work queue now has a few mutexes. It's got a lock for grabbing things off the queue, and I've also got this log lock, and the reason I've got that is just to synchronize the printing to the console. I just find it a little bit nicer. So if we want to print something out, we will grab the log lock and just print that out, because all of this stuff is going to be printing to the console. Okay, so this is the main concept here, is the fact that we have this infinite loop, and it just keeps continually trying to acquire the lock. So we can run this and give this a second to load up. There we go. Okay, so look on the side. I'm not doing anything, but my CPU is way up. Okay, that's not great. And what's happening is it's all those background threads are waiting continually. So I mean, if I launch this up, yeah, of course it goes fast, but the CPU usage is way up. So let me try that previous thing. We'll go. And this is actually very interesting. See that the CPU usage has decreased. Actually, it's a little bit random. There we go. So previously, I think we were on 59 seconds or something. We're now on 49 seconds. So that's an improvement. But what isn't an improvement is this amount of CPU wastage, because all those background threads are all waiting on stuff. We can also check that if we put in to end the program, we are successfully ending all the threads. So I'll talk a little bit about that as well. So the way this is working is we go ahead, we add to the work queue, and then the moment we add to the work queue, the background threads are immediately going to see that and start working on it. So what we're doing here, we have this loop which will just keep asking for jobs, add the jobs, and then what this loop is doing is just continually waiting for all of those threads to finish. In other words, it's waiting for the work queue to be done. So we try to acquire the lock, and then we work with the resource. And this is the big pattern that I want to look at. It's this infinite loop of try to acquire the lock, work with the resource, do some work, and then release the lock, which, yeah, it makes sense, it's logical, but it leads to that really high CPU utilization, which is just wasting power. So then my next question is, how can we make threads go to sleep when there's no work? And the answer to that question is basically condition variables. Now, a condition variable sort of is what it sounds like. It can signal, it can notify threads, and it can also be waited on. So if we go to the work queue, I've now added two condition variables. First of all, a job flag to indicate that there is work that needs doing. And secondly, a done flag to indicate that all the work has been done. So if we look down, we're going through the normal stuff. We're launching all of our threads. Okay. And now what we do is we get a number of jobs, like 10 jobs or something. And then, okay, no worries. So we go through 10 times and add a job. And for each of those, we get this job flag and we call notify one. Now what that does is, at least on my system, I've got 11 threads and they are all blocked. They're all waiting on this job flag essentially. So notify one will wake up one thread. What we could do, and this is actually, well, okay, I'll talk about this. So we could, instead of that, launch on all the jobs and then notify all, and that will wake up all of the threads. And that's, I found that was roughly equivalent for a large number of jobs, but then if I put on 2 jobs and I've got 11 threads waiting on it, then there's not really much point notifying all of the threads because not necessary. So instead I'll be doing this on a job by job basis. Okay, so we go ahead and we do that. And now what I'm doing here is basically waiting on a signal. So the way this works is, first of all, we acquire a unique lock on some shared mutex. In other words, just the work queue lock in this case. And then we call wait on the condition variable. And the arguments to this are the lock, the unique lock that we've made up above. And then this is a lambda function, which is the condition that we're waiting for. So we're going to keep waiting until the work queue is done, basically. And this is properly synchronized, right? It's not going to be randomly firing off because it's based around this lock here that we've created. And so if we get to this point and the code starts going from this point beyond, then that signal has been successfully registered, I guess, successfully fired off and caught by us. And until that happens, this thread will go to sleep, the main thread. And so right up above, we can see this in action as well when it comes to this operator. So yeah, we still are logging out like the thread started, it's ready to go. We keep going. Now, at the top of the loop, every time we grab a unique lock on the work queue, and then we wait. But, I mean, what's going to happen when the queue is, like, what am I thinking? Okay, what's going to happen when we want the program to end? We need to have some way that we're not just, this thread isn't just waiting indefinitely. So we'll do the same as before. Okay, so we'll wait on the lock, and we'll use this lambda function. So we'll wait until there's something on the queue, the work queue is not done, but we will put a time limit of 200 milliseconds. So when the program ends, there'll be a delay of 200 milliseconds while the background threads are still waiting to see if anything pops up, if that makes sense. But then if that doesn't happen, then we'll go to the next step of the loop. And in the next step of the loop, the code, probably this done variable, will have been set, and so the loop will end. I hope that makes sense. What we can see down here is really just the same stuff as before, except I guess this part here. So we grab the lock, same stuff as before, but then after we've done the job, we notify the done flag. And it could be that we notified the done flag, but then the condition that the main thread was waiting on is not satisfied. That's okay. It'll just keep waiting. It's, hopefully that makes sense. At one point, one of these threads is going to finish the final job, then notify the main thread, and then it will proceed from there. So enough teasing. Here we are. Okay, so before we had close to 100% utilization, and as we can see now, we have close to 0 utilization. Okay, so we can set some jobs. They get executed. Okay, excellent. We can set a lot of jobs. They get executed. And let's go with the benchmark. So watch this CPU on the side. Currently, no utilization. Then the CPU wakes up. And does its thing, and then goes back down to 0 utilization. Now note that the time to execute is about the same, 45 seconds. But at least we're not idling and wasting power. So then we can end the program, and those threads all end properly. Excellent. So I'm pretty happy with that. How can we speed it up? Well, let's have a look at that. This bit is a bit of a boo-boo on my part. I made a dodgy work queue, basically. And the issue with the work queue that I had is that because I was not quite trusting myself on the synchronization stuff, so I kept jobs on the queue even after they'd been completed. And that meant to check if the queue was done, we would have to search through all of the elements, which is a big O n operation. And then when you do that a bunch of times, it becomes a big O n squared operation. So that's really not good. And that's the main thing that was slowing it down. So here's the improved work queue that I've got. We just have 3 methods: push, pop, and done. So to push, we just add something on to the queue at the end. To pop, we just get the first thing and return it and remove it from the linked list. And then done, we just check whether we've got something in there at all. So that's the main thing. Nothing else really changes. I guess if we could look at the worker queue, it starts to get a little more logical. So again, we get the unique lock, and then we use that wait until. By the way, this returns true if it successfully got the lock, otherwise returns false. And then what we do is, we pop the job that we want to work on. So that gets removed from the work queue. And then, execute it, delete it. That's it. Yeah, there's something nice about that. But anyway, let's try this out. Okay, so just as before, we have low utilization, and then it goes up. And then you'll see this is very satisfying actually. As this keeps going, we are deleting those completed jobs. And so the memory goes up, and then it smoothly goes down. It's very nice. There we go. 21 seconds from 49 seconds. Now, you may notice that that was not great. Not great CPU utilization. And in fact, if we're doing something that takes like 60 seconds, for instance, and then we split it up over 10 threads, ideally we're not going to get 60 divided by 10, but we'll probably do a little better than 60 divided by 3. Now, my hypothesis here is that the limit is actually the std cout and acquiring a lock. So we have all these threads, but they are using a shared resource. We need to acquire a lock to the shared resource, which is basically the IO stream, and then work with that. And you'll also see, if I do this again, if you watch the threads, it's the same thread doing all this stuff, and it will change periodically. Or maybe it won't. In my trials, I was finding that it would stay on one thread for a while, then go to the next thread, and so on. And I'm not entirely sure whether that is actually what's going on under the hood, or if that's just the way that the printing is working. But anyway, many things to consider. I did find that when the job had a higher overhead, so there was more actual work to do, that the thread sharing was more even. But it could just be that if you're just simply printing out to the console and then you keep doing that, it turns out that one thread dominates because of that shared resource and the low overhead. But anyway, I am rambling, and why not? It's fun. But yeah, so that's my little job sharing system. And hope you got something out of that. I had a lot of fun putting that together, and I'll probably be using it in my stuff. Anyway, as always, have a great one, really, and I'll see you again soon. All right, bye.